Okay, so we're going to start. It is March 7th. And we're still looking at L'Hopital's rule. There's a little bit more we need to do with what we started last time. Then we need to talk about an application of L'Hopital's rule. And then we need to look at some other indeterminate forms. L'Hopital's rule. So, to get us started, we looked at a couple easy examples yesterday. Remember the basic idea of the rule. What are the two forms we must have so we can use the rule? 0 over 0 or infinity over infinity. You have one of those two forms. You need to state you have that form. Then you need to state so we can use L'Hopital's rule. And we get, how does L'Hopital's rule work? What rule work? What do we do? Done. Yes. And hopefully you noticed yesterday, this is not quotient rule or anything like that. It's the derivative of the top over the derivative of the bottom. We're not finding the derivative of the entire function. We're doing the derivative of the top over the derivative of the bottom. Let's take a look at this problem. Let's take a look at the limit as x approaches infinity of x squared over e to the x. Step one, what do? Plug in. Well, we can't really plug in infinity like a number, so what do we get, though, if we were plugging in something huge? Infinity over infinity. So because we have that, we can use L'Hopital's rule. So I'm going to say plugging in gives infinity over infinity. So use L'Hopital's rule. Okay, go do it. These are easy enough derivatives. Just like chapter 1, I will be picky about you using limits. Make sure you're using those properly. There will be a rubric question on the bottom of your quiz on this stuff. In addition to using limits properly, make sure you're also not plugging in infinity like a number. I never want to see e to the infinity or infinity squared. You can state it as an indeterminate form, but not plugging in like a number. Quasi question.
I think you said this yesterday. Do you actually want us to say so? Plugging in?
Yes, because that's what they're going to look for on free response questions on the AP exam. Okay, so now what do you have? What's the answer? Oh, well, plugging in gives infinity over infinity. We're going to do it again. Hopefully, though, you realize that that second problem is a little nicer than the first problem. The first problem had a square. The second problem just had an x. This one probably won't have, actually not probably won't, definitely won't have an x up top, so that'll be a little nicer. What's your limit? 0. E to a huge number on the bottom, 2 over a huge number will give us 0. The reason I needed to show you that one is just to show you that you might have to use L'Hopital's rule multiple times. And that's perfectly okay. As long as we're getting 0 over 0 or infinity over infinity, we're good. Next one. I would like you to take a look at the limit as x approaches 2 from the left of the square root of 4 minus x squared over x minus 2. See what you can do with this problem. Oh, I hope you use the chain rule. We'll go back and use the chain rule now. All our normal derivative stuff still applies. So I'm getting the limit as x approaches 2 from the left of negative x over square root of 4 minus x squared. Now what? Plug in. Okay, so we're going to get negative 2 up top. On the bottom, we get 0. How do we deal with these? This goes way back to September. Sabrina.
Since they gave us limit as x approaches 2 from the left, we just do like 1.99.
Yeah, so let's do that. Let's do 4 minus 1.9999 squared. Underneath the square root, you're going to get a very small number, right?
Yeah.
Small positive or negative?
Positive.
Well, that's really good because we couldn't handle the square root of a small negative. But we're going to get negative 2 over a square root of a small negative, square root of a small, no, sorry. Negative 2 over square root of a small positive. Square root of a small positive is still a small positive. So I'm going to say negative 2 over a small positive. What's the answer? Negative infinity. All those things that we did earlier in the year still apply. If you don't remember that stuff, I've got some examples of those in the packets that I just handed out. And also, please note that once I start plugging in, even though I'm plugging in something close to 2, no limits anymore once plugging in starts to happen. One more of these before we look at our next idea for today. I would like you very quickly, easy last one, I'd like you to do the limit as x approaches 0 of x squared minus 3 over x cubed plus 4. Take care of this quickly, and then we're moving on. What am I doing wrong? Whoa. Oh, okay, so we get 0 over 0, and then we do our L'Hopital's rule stuff. Good? Oh, you just plug in here. You're going to get 0 minus 3 over 0 plus 4. You're going to get negative 3/4, and that's your answer.
Oh my god.
A, L'Hopital's rule doesn't work if you don't have 0 over 0 or infinity over infinity. And B, if you try to use it when you don't have one of those forms, you're going to get a very wrong answer. Always plug in first, and if you don't get one of those forms, that's just your answer. Make sense?
Yes.
I'm almost certain one of these is mixed in the homework, and I'm also almost certain that I will put one of these on our L'Hopital's rule quiz. Don't automatically use it. Make sure you're checking your condition first. Next thing we need to talk about is called relative rates of growth, which I think sounds much harder than it actually is. Relative rates of growth. And we're going to be looking at things like what grows faster. Y equals x squared or y equals x cubed. I haven't really defined what it means to grow, but what would you guess? X cubed? Okay, maybe. What about y equals x squared or y equals e to the x? I don't know. Maybe e to the x? Okay, I don't know. What about y equals the natural log of x? Or y equals the square root of x? What grows faster there? Well, those are both answers. One person said square root of x, one person said natural log of x. So we need to define what it actually means for a function to grow faster than something else. So here's how this works. Definition. We're defining growth rate of these functions. If f of x and g of x, first of all, are positive functions, at least when x is large, then we have 3 cases. So you can't see that. There we go. If the limit as x approaches infinity of f of x over g of x equals infinity, the function on the top is going to grow faster. Then f of x grows faster than g of x. You're plugging in a huge number, the top is huge, the bottom becomes something that you can handle. The top is bigger, the top is growing faster. Second case, if the limit as x approaches infinity of f of x over g of x equals 0. That means you've got some number up top and something huge on the bottom. That means the bottom is growing faster. G of x is growing faster than f of x. Are there any other things that could equal besides 0 and infinity? 1. That's 0. It could equal basically any other number between 0 and infinity, which isn't really a number anyhow. If it equals some number, that's not 0 and not infinity, then we're going to say those two functions grow at the same rate. If the limit as x approaches infinity of f of x over g of x equals, I'll say L, a non-zero number, then f of x and g of x grow at the same rate.
What if it's
Well, it's not really going to be 0. It's going to be like some number over a really small positive, which will basically give us infinity. That's our first case. Move that there. For our first example, we are going to compare the two functions y equals x squared and y equals x cubed. You already said that it seems like y equals x cubed should grow faster, but now let's actually test this thing and see what's going on. Well, I'm going to set up a limit. So I'm going to do the limit as x approaches infinity of x cubed over x squared. We're doing this in this section because oftentimes this will involve L'Hopital's rule. You need L'Hopital's rule here? I think we could just simplify this thing. Why don't we just make this problem the limit as x approaches infinity of x? What's that? Which grows faster, the top or the bottom? X cubed grows faster. Now, if instead you set up this problem so it was x squared over x cubed, you'd simplify that to 1 over x. Your limit would be 0, which means the bottom grows faster, which is still x cubed. Doesn't matter how you set things up, you'll still get the same answer of what is growing faster. Okay. We are going to compare y equals e to the x and y equals x squared. Limit as x approaches infinity. What do you want to put up top? Okay. If you said e to the x, you wouldn't be wrong. But we'll do x squared up top. What do you got? Infinity over infinity. So what do we have to do? L'Hopital's rule. So, plugging in gives infinity over infinity. Use L'Hopital's rule. I actually feel like we've done this exact same problem earlier today. You're going to use L'Hopital's rule. You're going to get 2x over e to the x. Do it again. Because plugging in gives infinity over infinity. We are going to once again use L'Hopital's rule. That's not our rule. Which one? E to the x. Our rule is if the limit gives us 0, then what was in the denominator grows faster. So our answer is going to be e to the x grows faster. 0, the bottom grows faster. Infinity, the top grows faster. Any other number between 0 and infinity, they grow at the same rate. No. Is this not like super hard? I just kind of needed to show you how this works. You're going to try one more. Whatever. I was going to give you one where we got 3/7 for an answer. If you got 3/7 for an answer, what grows faster? They grow at the same rate. Okay. Next. We talked about 2 indeterminate forms last time. However, there are more indeterminate forms than that. You know what? We're just going to start a new sheet. More indeterminate forms. We have 0 over 0. We have infinity over infinity. If we have something in one of those two cases, we can use L'Hopital's rule. But there are some other forms that are indeterminate. If we get one of those forms, we don't know the answer right away. For example, 0 times infinity is an indeterminate form. Because what's 0 times anything? 0. But what's like infinity times anything? Should be and really, we're talking about limits here. So it's really like saying, what's 0.000001 times a huge number? Well, probably a huge number, but maybe the 0.0001 is big. We can't really decide, will this be 0, will it be infinity, or will it be something in the middle? It's an indeterminate form. Another indeterminate form, infinity minus infinity. Okay, would you agree that like 2x is greater than x? But if we plug in like a huge number to 2x and a huge number to x, huge number minus a huge number, they're not just going to cancel out because the 2x one was a little bit bigger. Infinity minus infinity might give us 0, might give us infinity, might give us something else. Next, 1 raised to the infinity is an just wait, this gets good. 1 raised to the infinity is an indeterminate form. If you have 1.00001 raised to a huge number, 1.0001 times 1.001 times 1.0001 times, it's going to get big, very slowly, but it will get big. What if you have 0.99999 raised to a huge number? It's going to get very small. So it depends on how we're approaching these things, which is really why these are all limit problems, but that's another indeterminate form. Here's one that goes back to algebra 2, 0 raised to the 0. Anything raised to 0 is 1. But you also know that 0 raised to anything should be 0. And in algebra 2, you would have said this problem doesn't exist, and 0 to the 0 still does not exist. But we can talk about limits that are in that form and actually figure out what those numbers end up being. Another one is infinity raised to the 0. Another indeterminate form. The idea is, with those 5 forms at the end, problems in those indeterminate forms need to be reworked, rewritten, so we can use L'Hopital's rule. Problems in these forms need to be rewritten, so we can use L'Hopital's rule. And again, L'Hopital's rule only applies if we have 0 over 0 or infinity over infinity. So if I have one of the other forms, I want to try to do some algebra with that thing to make it 0 over 0 or infinity over infinity. And there are really 3 different types of tricks we need to be able to deal with. I'm going to zoom out a little bit so we can still see that. The first example we're going to look at is the limit as x approaches infinity of e to the negative x over the square root of x. By the way, you might want to have out those sheets of graphs that I gave you yesterday, just to kind of help us with some of our initial evaluating, initial plugging in. Okay. Yes? Oh, go with what I wrote this time. Limit as x approaches infinity of e to the negative x times the square root of x. Thank you. Might have given something away, but whatever. Okay, you're going to plug in a huge number. What's e to a negative huge number? 0. 0. That's like saying 1 over e to a huge number. That's 0. What's the square root of a huge number? A big number. This is something in our form, 0 times infinity, which is an indeterminate form. I need to rewrite this. Matthew, what do you think? E to the negative x, wouldn't that just be e to the x in the denominator? Yeah. Let's rewrite that. This is the limit, as x approaches infinity, of the square root of x over e to the x. Okay, well, plug in a huge number. Square root of a huge number is a huge number. E to a huge number is a huge number. Plugging in here gives us infinity over infinity, which means you're allowed to use L'Hopital's rule. So please go do that. Okay, just go work. We should be working, not making sounds. Just work. Do you have an answer? 0. Because all the big stuff now is in the denominator. 1 over something big will give you 0. The trick will always be, if you have 0 times infinity, well, let's move one of those pieces to the denominator so I can get either 0 over 0 or infinity over infinity, and then I am allowed to use L'Hopital's rule. Let me show you another one like this. Okay, so first of all, I guess we're dealing with our 0 times infinity case. I guess I should have labeled that earlier. These two examples will deal with how to work with that. Limit as x approaches infinity of x times the sine of 1 over x. Bless you. Can I move up so we can see that bottom problem? Is anyone still copying the last problem we did? Okay. We're going to look at this problem. We're going to get infinity times 1 over a huge number is 0. What's the sign of 0? This is that infinity times 0 or 0 times infinity form. I need to move something to the bottom. This is not as obvious. I could turn sine into 1 over cosecant. That's not actually going to be the way to go. Watch what I'm going to do. Rather than saying times x, I'm going to say divided by 1 over x. Isn't dividing by 1 over x the same as multiplying by x? Can you kind of convince yourself of that? Multiply by the reciprocal, you get the x there. This is actually going to be what we need to make this work. This is the limit as x approaches infinity. Well, no, sorry. This gives 0 over 0. So use L'Hopital's rule. I'll be picky about this, so I need to be picky about this. I know. We should definitely not forget this. The derivative of this one, the cosine of 1 over x. But that's not it. What was that? Negative 1 over x, where we're using power rule on this thing. We're using chain rule to do the derivative of x to the negative 1. That's negative 1 x to the negative 2, negative 1 over x squared. In the denominator, what's the derivative of that thing? You already did it. Negative 1 over x squared. What did you just say, Casey?
Those cancel.
Those cancel. That's kind of why I did that. I'm going to get the limit, as x approaches infinity, of the cosine of 1 over x. It's not part of a sum that I'm canceling. It's part of a product that I am allowed to cancel. This becomes, okay, 1 over a huge number is 0. This becomes the cosine of 0, which is 1. What this is really saying is if we had this function and graphed this function, x times the sine of 1 over x, and looked way to the right on the graph, those y values would be getting close to 1. That's what it's really saying. Okay, do you get the 0 times infinity case? You move 1. Okay, wonderful. Next case to deal with. This is probably the easiest of the cases. Infinity minus infinity is our next case. For example, the limit as x approaches 1 from the right of 1 over the natural log of 1. Nope, sorry. White out. Forget this. We're just going on the back. We're going to try this again. Okay, hush. Limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. We want to do the limit. Okay, so I'm going to plug in something a little bit bigger than 1. What's the natural log of a little bit bigger than 1? Close to 0. So 1 over a small positive, that's going to give you infinity. Minus, plug in something a little bigger than 1 over here. What's that going to give you? Small number. 1 over a small what? Small positive or negative? Positive. 1 over a small positive is also a small positive. No, it's not. 1 over a small positive is a huge number, is infinity. We're getting infinity minus infinity. It is this case. Anyone want to take a guess what we could do? Make it one fraction. Get a common denominator. Let's turn it into one big fraction. That should give us 0 over 0 or infinity over infinity. So just get a common denominator. We're going to get the limit as x approaches 1 from the right of x minus 1 minus the natural log of x over the natural log of x times x minus 1. At this point, if you go and plug in your 1 minus 1, 0, minus the natural log of 1, 0 on the top. Natural log of 1 is 0, this is 0. Plugging in gives us 0 over 0, so now we can use L'Hopital's rule. The trick with infinity minus infinity is really just get a common denominator. And of course, when you use L'Hopital's rule, what do you have to remember on the bottom? Product rule. Please do that. And then maybe wait after you do the derivative, because I feel like there will be a little more work we should probably talk about together. What do I want to do? Why don't I just say it like this? Can you get something that looks like that inside your limit? 1 minus 1 over x. 1 minus 1 over x all over natural log of x plus 1 over x times x minus 1. Let me just plug in, because maybe if I plug in, things will just be good, and I can kind of go from there. Plug in 1. This is not looking good, though. 1 minus 1, 0 on the top. That's a 0. This is 0 times 1. We're going to get 0 over 0. So I need to kind of clean this up a little bit. How about let's do that. Let's get rid of our fractions inside fractions. Let's multiply this thing by x over x. So we're going to get the limit as x approaches 1 from the right of x minus 1 over x times the natural log of x plus x minus 1. Plug into that. 0 over 0, but yeah, I can do the derivative of this. I can use L'Hopital's rule. Plug in, you'll get 0 over 0, use L'Hopital's rule again. This should be the last time you have to do this in this problem. Yeah, I definitely know I'm going to be done at this step because I've got a 1 up top. Can't get 0 over 0 or infinity over infinity. I'm actually getting a kind of nice fraction here. Are you getting 1/2? Limit is x equals 1 from the right. We should have x times 1 over x in the denominator plus the natural log of x times 1. Product rule on from that thing. Plus 1 at the end. 1 over 1 plus the natural log of 1 plus 1. 1 over 1 plus 0 plus 1. 1. Yes. Well, okay, I didn't realize we had to use L'Hopital's rule a couple. I guess the easy part is turning it into a good form. We get a common denominator. So the good news about the other 3 forms is they really work all the same way. The bad news is I need like 10 minutes to do that. And I don't have 10 minutes right now. So we will pick up that next time. I'm going to stop this, and I need to stop this the right way because last time I didn't do it right and lost everything. Where is the... Oh, it's just this button.